Good morning, students. In today's session, we will be dealing with a specific problem that we face in relation to effective memory management organization, and that is the concept of thrashing. So basically, in the last sessions, we have already covered the different types of page replacement algorithms. Say, for example, FIFO or optimal page replacement or least recently used page replacement algorithms, and today we will deal with a specific phenomena, that is the phenomena of thrashing. So we will look what is thrashing and why does thrashing occur. So as you have studied in the previous sessions that after the implementation of the virtual memory concept, we are considering the contents of a particular process in terms of some pages. So basically, we are loading the pages of a particular process from the secondary storage to the main memory. And along with that, we can also start a process with only loading a few of the pages into the computer's physical memory. Now, those pages are to be located or are to be stored at specific fixed size partitions which are known as frames. So basically pages are converted into frames inside the physical memory. Now what is happening is that let's take an example that a particular process has been allocated some amount of frames, but it is not been allocated with enough amount of frames so that it can proceed without any sort of disturbances. That means the number of pages that it needs and the number of frames it has been allocated, there is a mismatch between the two. That means the particular process is getting uh, less amount of frames than it actually requires for seamless processing of the entire process. Now what happens is that if the process does not have the number of frames it needs to support the pages in active use, then what will happen? It will quickly quickly result in a certain page fault, and at this point it will have to replace some page. Now as it is been allocated only a few frames, that means whatever pages it is working with all are active pages. That means the particular process requires those pages frequently. Now if that is the case, then what will happen? Since all its pages are in active use, it must replace a page that will be needed right again away. So consequently, it will again create a fault in future, and again, and replacing pages that are already in current use, and those pages also needs to be brought back into the memory immediately. That means the particular process will be executing a high amount of paging activity. So this high amount of paging activity is actually called as thrashing. So a process is thrashing if it is spending more time paging than executing. Now, why is this happening? Because the particular process is being allocated a certain amount of certain number of frames, but that particular number is not enough to execute the process without any sort of interruption. So that is the case here. Though we are increasing the degree of multi-programming by bringing in more processes active in the memory at the same time. Now for doing so, we are allocating few or a fixed number of memory frames to each of those processes, and that particular allocated number of frames may not be enough. So in that case, thrashing may result. So how can we limit the effects of thrashing? Basically, we can limit the effects of thrashing by using a local replacement algorithm or priority replacement algorithm. Now, with local replacement, what is happening here? If one process starts to thrash, we ensure that it cannot steal frames from another process, and which may lead to the latter process also to thrash. That means whenever a particular process is thrashing, we are preventing it from taking away frames from other processes. So by doing so, what we are ensuring here, a particular process which is thrashing will not lead to the thrashing of another active process. Now, the problem is not entirely solved here. See, if the particular processes or if the process is thrashing, they will be in a queue for the paging device most of the time. Now, in that case, the average time for a page fault will also increase because of the longer average queue for the paging device. So ultimately, the effective access time will be definitely increase even for a process that is not thrashing. So whenever the particular process, whenever the system is being busy with a lot number of thrashing or thrashes, then what will happen? It will increase the effective time of not only the processes causing the thrashing and but also the particular processes which are not contributing to the phenomena of thrashing. So both of the processes, both of the types of processes will be affected in case of thrashing. Now, to prevent thrashing, we must provide a process with as many frames as it needs. But how do we know that how many frames a particular process will be needing? So there are several techniques. The working set strategy starts by looking at how many frames a process is actually using. Now, this approach defines the locality model of process execution. So basically, we are generally segregating a particular process into different areas of locality. That means whenever a particular process executes in a particular locality, then we may just assume that for a fixed amount of time, it will only be confined within that locality only. So the particular process's code can be divided into separate locality areas or models. So basically the locality model states that as a process executes, it moves from locality to locality. A locality is a set of pages that are actively used together. A program is generally composed of several different localities which may overlap also. Now take the concept of a simple program. Suppose you are writing a C program. So how do you organize the program? You organize the program into separate functional modules. So whenever the execution of a particular process enters into one particular function, so until all the instructions of that function are completed, generally the program is confined within that function only. So that is the concept of locality model here. So now in the slide, you can see a diagrammatic representation of the concept of thrashing. That means whenever we are increasing the degree of multi-programming in the horizontal way, at first the CPU utilization, which is shown in the vertical manner, it is increasing. But after a certain point of time, when thrashing happens, then suddenly the degree of multi-programming uh, reduces to a much huge extent, and uh, it just got in a downward manner. A downward fall happens here. So that is a graphical representation of the concept of thrashing. So now we will review the locality model. When a function is called, it defines a new locality, as I told you. In this locality, memory references are made to the instructions of the function call, its local variables, and a subset of the global variables. Now, this particular idea is just a representation that a user uh, sees while writing a particular program. Now, when we exit the function, the process leaves this locality since the local variables in the instructions of the function are no longer in active use, and we may return to this locality later. Now, you already know that a particular function can be called numerous number of times in a particular program. So we see that localities are defined by the program structure and its data structures. The locality model states that all the programs will exhibit this basic memory reference structure. So whatever may be the type of your program, it can be a very simple program to a very complex program. The basic data structures The data structural models remains the same, and the execution is being followed with keeping those things in consideration. Now see, suppose we allocate enough frames to a process to accommodate its current locality. Then what will happen? It will fault for the pages in its locality until all these pages are in the memory. Now when all the pages are in the memory, then no longer it will uh, result into any sort of faults here until the locality changes. So this is the concept of the locality model. So if we can allocate enough number of frames to actually contain an entire locality in the memory, then no more page faults will happen. And if we do not allocate enough frames to accommodate the size of the current locality, then what will happen? Then the process will thrash. Why they will thrash? Because we will not be able to keep in memory all the pages that it is actively using. So that is the entire concept of thrashing. So it's a very short topic. So with that, we will be concluding our today's session here. So thank you.